Good morning. I know you're all ready for lunch. I'm Bill Bain from Scale Out Software. I'm going to talk about operational intelligence using in-memory data grids and how in-memory computing allows you to obtain insights on fast-changing data using in-memory computing technology. So let's look at who's presenting. It's me, Bill Bain from Scale Out Software. I've spent my career in parallel computing, going back to Bell Labs, Intel, Microsoft, and then Scale Out Software. And interesting, was anybody here for the previous talk with times 10? Because the first person I consulted when starting this company was the founder of times 10, interestingly, many, many years ago, 2002 or 3. So in fact, it was very interesting to look at the difference between SQL-based in-memory database and a NoSQL in-memory data stored, in-memory data grid, which is what we produce. So Scale Out Software creates in-memory data grid technology for two purposes. One is to store fast-changing live data so that you can accelerate applications by scaling out across a cluster of servers. And the second purpose of this technology is to allow analytics or analysis on fast-changing data so you can detect trends in real time and provide feedback to a live system. That's called operational intelligence, and that's what we'll talk about. So the purpose of this talk is not to talk about our technology. It's to talk about how we've applied in-memory computing techniques to some real use cases out there that we've encountered with customers since 2005, and to show you how this technology can solve real problems for providing operational intelligence. So there's several examples, and hopefully there'll be time at the end to do a quick demo by my colleague here, Oleg Schmidtov. So this is the agenda, and we'll first talk about how in-memory data grids are used for data storage, and then we'll look at how they've been used in the early days for query. We just saw in the times 10 the microsecond with 2 microsecond select. In-memory data grids scale out across a cluster of commodity servers. There's inherent network overhead for query. We'll talk about that in a minute. And so you're not going to see a 2 microsecond query time. In fact, what people have learned is to achieve high throughput with relatively low latency, it's important to actually use data parallel computing techniques, because data parallel computing allows you to operate on a large set of data very quickly to obtain fast results and return them to a live system. And we'll see how that's different from the traditional use of data parallel computing in technologies like Spark, and previously to that Hadoop, and previous to that parallel supercomputers, in order to work on offline data, and how in-memory computing allows you to bring that data online. This all reinforces the theme that we heard from Abe this morning in the keynote about the digital revolution and how in-memory computing can allow us to do new things with data that we thought previously could only be done in the data warehouse offline, and that by obtaining this intelligence in real time, we can solve a lot of problems that are very challenging when you don't have in-memory computing. So let's first talk about in-memory data grids and what they are. So I'm sure most of you are familiar with this technology, but if you're not, in-memory data grids are storing live, fast-changing data in memory. They have the logical view, and by the slides, I'll be happy to just send you, just let me know and I'll send you the deck if you need them. And I think they post them too after the conference. So they're storing objects which correspond usually to an object-oriented programming language like Java or C#, C++. So they're business logic state objects that are fast-changing. It's not a SQL view of data. It's a NoSQL view based on key value store. And so the objects are accessed by key using very simple APIs which have been called CRUD, create, read, update, delete, a lot like file system, except non-hierarchical storage. In fact, objects are typically stored in collections, generally by language-defined type. So if you have cars and generators, you would have 2 collections, a cars collection, which has a lot of objects representing cars, and maybe another namespace representing people or generators or windmills or whatever. We've been doing a lot of work in stream processing, so I tend to use IoT examples these days. In any case, what we're getting from an in-memory data grid is scalability, transparent scalability, and yes, they do use partitioning or sharding to scale data storage across a cluster of servers with a common membership, and also high availability, so through data replication. One technique for replication is quorum-based replication, and one of the areas in which our company has some technology patent is on quorum-based replication of objects on a logical basis across a cluster of servers. You might find that patent interesting to look at because it allows us to have quorum reliability for doing updates, but do so on a cluster of servers which are just viewed as a physical resource. So in any case, what you're getting with an in-memory data grid is very fast, scalable in-memory data storage with low latency access. And that allows this to be used to store numerous types of data in many applications. The classic application that we have encountered is shopping carts for e-commerce. But there are many other examples, news stories for an online reporting service, airline reservations for a major airline down at the bottom there, medical records for a medical service company, entertainment for online gambling. So many applications for fast changing data. Typically, our customers, we went to market in 2005 and been in there ever since. Most customers think about in-memory data grids as a passive storage cache. In fact, they typically want to use query because they come from a database world. The Times 10 gentleman, Sam, gave a very compelling argument as to why everything should be a SQL query going all the way up into the application. But I think there's a case to be made for storing data in an in-memory data grid based on an object-oriented view of that data, because that's what the application is actually working with, and avoiding the object relational mapping, except when you're going to store the data for long-term persistence. And so in-memory data grids provide not a SQL view or relational view of data, they provide an object view of data, as I just described. And so even though one can do query in a SQL style by querying on properties or tags associated with objects, that tends to encounter a fair amount of overhead because every server has to be touched in order to see if the objects that are desired are on that server. That's an order in operation if you have n servers. And so it's in comparison, if you just do a read of a single object, that's an order one operation. So what we found is that we are often discouraging customers from using parallel query and instead move to data parallel computing, and that's what we'll focus on in the next slide. But there is an intermediate step you could think about, which is, okay, so we're going to allow you to do a parallel query, but then we're going to ship out a method that can be run against all the queried objects and run in the grid to actually say, do I really care about this object? So I can run some application-specific method, for example, looking at if this is holding stock price history, looking at the alpha and the beta of those stocks and see whether or not you really want that object to be returned to the client, and do this something that's much more specific than you could do by just doing property-based query. So that's an example, a very simple example of data parallel computing. You're moving some of the analysis into the grid, but you're still returning the objects of interest. So we're going to talk about why you would want to do parallel computing in the grid, and then some examples of how we've applied it. So the real purpose is this concept of operational intelligence, which is the ability to obtain very fast feedback for a live system and return that feedback to the system to optimize operations or capture opportunities that otherwise would be lost. And there are many applications for this, as you can imagine. One that we'll see hopefully in the demo is personalized real-time recommendations. One that I think is completely untapped that's very interesting is security systems, looking at security perimeters and trying to make decisions with fast-changing telemetry as to whether there's an intrusion. But fraud detection for credit card transfers, IoT, stream processing for IoT, where you're actually analyzing the events that are coming in from devices and then providing feedback. We'll look at some use cases of that. Many uses of analyzing live data in the live system. I'm giving a talk tomorrow on the use of the digital twin model for stream processing, and we talk about the Lambda architecture. But if you guys are familiar with the term Lambda architecture, what's interesting here is most people think about doing this kind of analysis offline through a database, typically with query. But in fact, with an in-memory computing technology, you can bring it into the live data, bring the analysis to the live data, and get the results much faster. So it causes you to rethink what you're doing with the data that's changing rapidly. So as I'm saying, the traditional technique is business intelligence on the right. That's evolved from Hadoop, more recently Spark. And these are technologies which, even though they have, in Spark, you can have memory-based data sets. We're talking about very large offline data sets that are viewed as being in the data warehouse and being analyzed offline to find strategic patterns and trends. Whereas with in-memory computing, you can move towards real-time operational intelligence on live data sets that are changing even while you're doing the analysis. So you can think about doing a data parallel operation on data that's actually changing during that operation, and you're just capturing a snapshot to see what the patterns and trends are on that data and providing immediate automated feedback without a human in the loop. So the benefit of this is reduced time to action, right? So if with business intelligence, the time to action can be very long, so opportunities in real time can be missed. Whereas with operational intelligence from in-memory computing, you can capture opportunities much more quickly. And that's because you're working on the live data and you're making automated decisions. All right, so this is one technique for data parallel computing that we put in our product. I came out of Intel supercomputer systems, and we worked with supercomputers at the national labs for many years. And there are technologies like MPI that had the built-in data parallel execution platforms. So it seemed very natural to adopt those to an object-oriented view, adapt those to an object-oriented view and run them in an in-memory data grid on the objects stored within a collection in the grid. And so we call this a parallel method invocation. It's basically the simplest thing you can imagine for data parallel computing. So what you do here is you create a method that you run as an evaluation method on all the objects that you query in a collection distributed across all the servers of the grid. And then that method execution creates a result, some kind of analytics result, which you can then merge. And you could do a binary merge in logarithmic time to capture those results into one result object, which you return back to the client application. And by doing this, you can, first of all, build much more complex data parallel operations like MapReduce. That could be built with 2 phases of PMI. But what you're able to do here is move code to the grid for execution, as opposed to querying the data and pulling it out of the grid and running it sequentially outside of the grid. So if you look at those 2 approaches, the one on the left is parallel query. In parallel query, we go select objects in a collection on the grid servers, and we have to ship them across the network with all of the overhead attendant to that. Whereas in comparison with data parallel computing, we just ship the code to the grid, do all of the execution in parallel with high scalability, and then just return the result object, that little black circle, back to the client. So you've reduced the network traffic, and you've also scaled out the analysis. It's kind of a no-brainer. But believe it or not, it's very hard to explain to customers many times when they have a mindset of, oh, you're a cache, you're not an in-memory computing platform. So it's a changing the people's way of thinking in order to get the benefit. So here's one example, the first example of about 5 I'll show you, and that's doing stock backtesting in financial services. This is a benchmark we did about 4 or 5 years ago now. So the numbers are almost a little bit antiquated by today's standards in terms of memory capacity and speed. We ran this at Amazon to demonstrate that this could be run on 75 servers to handle a terabyte's worth of data. At the time, that was a pretty large amount. What we're doing here is holding stock price histories in objects in the grid. So every object represents a stock like IBM or Amazon with all of the histories. But the wrinkle is we're providing new stock prices in real time. In this case, at 1.1 gigabytes per second, we're updating the grid's data. So the stock prices are continuously upgrading. At the same time, what we're doing is analyzing each of the histories based on a set of algorithms for testing what trading strategy we might want to employ. And then we can make deductions. If stock prices are changing today very rapidly, we can make a deduction about which trading strategy would be the best one to apply today with the current conditions, and then employ that strategy moving forward, and doing this in real time. And all this is demonstrating is that you can do this kind of operation in an in-memory data grid very rapidly. In 4.1 seconds, you can go through all of that data, and it's a little sublinear. I think there's a laser pointer, but yeah, interesting. No, okay. Anyway, it's the green line represents the scalability, and we think that the knee of that curve is due. Actually, this is run on Amazon. We think it's the spreading between 2 chassis, and so there's network overhead between the chassis in the data center. But the top line represents no updates, and you see that's purely linear. So what you want to achieve is linear scaling of throughput as the workload increases. This concept of scalable throughput. for you people who go back to Amdahl's law of scalability, this is called Gustafson's law or Moeller's law. It's scaling the throughput of a system by increasing the workload and then increasing the number of servers to handle that workload. And what you get for that is constant latency for any given operation, even though the workload is increasing. And if you think about it, say for e-commerce shoppers, getting recommendations is exactly what you want. You need to get recommendations in a certain amount of time, but you may have 100,000 customers or 1 million customers, but nevertheless, you have to keep the latency fixed. So if you don't have scalable throughput, what you get is this tailing off of the throughput, the blue line there, and that's generally caused by network overhead. So if you treat an in-memory computing system as a cache and just pull all the work into the client, then you have so much network overhead that you get this result. This is also stock backtesting in a different experiment to demonstrate the difference between running the algorithm in the grid or accessing the data and running it outside of the grid. So, pardon me, data parallel execution runs within each server of the in-memory data grid, doing the query, selecting objects, and then putting that through an in-memory execution engine that uses all of the cores in parallel to do these eval operations, these class method execution, to evaluate those queried objects, and then merge the results within that server. And so that's done on all of the servers, and then the result is merged using a log binary tree to do that in logarithmic time. That's one of the lessons from the early parallel supercomputers. I don't know if you have looked at the history of supercomputing, but the earliest parallel supercomputers actually physically built a binary login network until people realized you can't scale that in a physical world. We live in a 3D world, and building an order in-dimensional network in a 3D world is a big challenge. But logically, a binary tree gives you the fastest combining time. So here's another example that we ran across with a hedge fund, where the goal of this hedge fund, and one of the interesting aspects of this, and you'll see this thread through each of the examples, is that the challenge for each scenario is what is the domain for data parallel execution? In other words, what piece of work do you use to subdivide the data parallel execution across? We call it a domain. And that seems obvious, but in most cases, before you know the answer, it's a head scratcher. So let's take this hedge fund, and it has portfolios of stocks in different market sectors like high tech, real estate, energy, and banking. And so each portfolio has a set of long positions and a set of short positions. And the idea here is to, using a proprietary hedge fund specific algorithm, rebalance those positions continuously during the market day. This particular hedge fund was storing all of this data in SQL Server and pulling it out every 15 minutes to try to figure out with the market changes what they had to do manually. And so what we said is, I think we could do this a lot faster for you in the grid. So here's how you do that. So the domain here would be what's called a strategy or a portfolio. So a given market sector, you would create an object in the grid and store all of the positions. And you can see that the circle at the top there of the long and the short positions. So that represents high tech. Now each strategy or portfolio can encapsulate a proprietary algorithm, right? The hedge fund says, well, our high tech strategy is this, our real estate strategy is that. One of the interesting aspects of this data parallel execution model being object oriented is it's very easy to encapsulate application specific algorithms in that model and just hide them from the orchestration that the grid is doing. We're just shipping methods out and running them, but we don't have to know what they're doing. In fact, in many cases, the customer doesn't want us to know what they're doing. They just want to run their proprietary algorithm. So in many senses, an in-memory data grid is an orchestration platform for data parallel computing. So the second piece of this is you take the market feed and you can break it up into, say, 1-second snapshots of all the price changes in that second, and then do a data parallel operation across all of the strategies with a given market snapshot. And so that causes all of those portfolios to be analyzed and updated. And the ones for which you violate the hedge fund's positions, they has to be rebalanced, then an alert can be generated. So the merge operation is simply collecting the set of portfolios that need to be rebalanced. In this particular case, they wanted a human to actually do the rebalancing. But this could be fully automated, of course. All right, so then what we did is produce just a UI for them, and the strategies are on the left. This is a synthetic UI just to show them the scalability, and the highlighted ones are marked in yellow, and then they can click on one of those and look down and see which positions are out of balance and which stocks need to be bought or sold based on their strategy. So what we're able to do is see that this could be accomplished for several thousand portfolios in about 350 milliseconds, and hence a market snapshot every second could easily be handled and checked to see whether rebalancing is needed. So we actually, at this time, we were doing this in about 2012, we were comparing that to Hadoop. Hadoop was taking about 15 seconds to do the same operation because of its batch processing view of data parallel computing. So you could see that moving the computation to the data with low latency, you can have real-time operational intelligence on that data. So here's another example we ran across for a perishable goods company. This company is selling perishable goods like flowers and fruit baskets, and the problem they had was that they would get orders, especially at busy times of the year like Mother's Day and Christmas, and they had inventory changes, which are in the perishable goods business. The inventory changes are occurring very rapidly. Many are failing, to materialize. Other, inventory is spoiling, all kinds of problems. So inventory changes are occurring rapidly. They had to reconcile in real time orders with actual inventory, especially inventory at a future date. And make sure that they could fulfill those orders. And what they found is a lot of their return was being reduced because of the fact of failed orders. They'd have to give credits to customers. The technique they used, they had two database systems that were siloed from each other, and one had orders, one had inventory. So they said, let's just dump all that into the grid into two namespaces. We'll create a compute cluster, and we'll suck all that data out of the grid using parallel query, and then we'll reconcile. And what they found is it took more than an hour to do that because of the fact that they're falling into the trap of doing parallel query. So here's a case where Oleg and I went and talked to them, and see if you could tell me, what should the domain for data parallel computing be in this case? Should it be orders? Should it be inventory? We don't have much time. In fact, I'll check my watch. But you got a guess? Okay, the guess is the SKU. So we came up with the idea that why don't you organize this data by SKU in the grid, so the objects shouldn't be order objects, they shouldn't be inventory change objects, they should be SKU objects. And then when orders and inventory changes occur, just go do CRUD-based updates, read update of those objects. So what this is essentially doing is pre-joining orders and inventory by SKU. Now you could do a data parallel operation by SKU, one operation, and in just less than a minute in their case, you can determine all the reconciliation, and if there are problems, generate all the alerts and return them to the person who has to make the decision about what to do about it. So you've reduced a problem that they were running once overnight, taking more than an hour, to something that's could be run in several seconds. It was interesting because we described this, talked about it for a couple hours, and they ran off. We had flown down there. They ran off and coded it and came back and said, problem solved. Data parallel computing, that's the way to do it. So it's another example of how getting rid of query and rethinking how do you analyze fast-changing data with data parallel techniques can lead to a much faster results and therefore real-time feedback. Well, here's another problem we ran into. This is a financial services company that was analyzing columnar data they were storing in our grid, and they wanted to run a method, a class method, again, object-oriented view, but on a specific object in the grid. So this is like a stored procedure, nothing magic about that. They needed a very efficient mechanism so they could do an algorithm, as you can see up there, where they're doing their very proprietary algorithm on those columns, getting the result, and then combining those results in the client. So we extended our data parallel computation engine to support what we call single method invocation instead of parallel method. And therefore, they can solve this problem very easily. Now, the reason I bring this up is it turns out there's an evolution here that I think you'll find interesting, how this leads into using an in-memory data grid for stream processing. We'll see how in 2 or 3 hops we get there from this. This was a financial services problem that we're just trying to solve with data parallel computing in the grid, because they need to run many of those at the same time. So the way this is sort of a step aside here to say, how do you implement data parallel computing in an in-memory data grid? It's interesting. The way that we selected to do it, which I think has advantages over the technique, some in-memory data grids like Redis do Lua scripting inside of the grid server itself where the data is stored. We felt that that has several limitations. One is you can only view the data inside of that server. Number two, if a user-based script fails, it could blow up the whole server. And three, that you can't support other languages like Java and C#. So we came up with the idea of let's create a set of worker processes, one for each grid server, that's hosting a runtime, say a JVM or a .NET runtime, and then we can ship code directly to those grid servers, IG worker processes on the grid servers, and run a data parallel computation in parallel. And so that technique has the advantage that it allows the user code to be automatically shipped. It allows that code to follow the object-oriented model of the grid and access any object anywhere in the grid. So you can build all kinds of interesting things like MapReduce with this execution platform. And also, it scales very naturally, and it enjoys the high availability of the grid itself. In fact, we have another patent that was just granted last year for how do you make sure that a data parallel computation is highly available. If you think about it, that's a very interesting problem too. If it gets partially done and then a server fails, well, what work failed and what work completed? And how do you restart that? Do you have to start from the beginning? So there's some things you can do that are interesting, but that's not in this talk. In any case, so that's how we execute both parallel method invocations and single method invocations. So this would be a parallel method invocation, just shipping the code out to the grid, running it in parallel, getting a result. And then multiple single method invocations, which can then be used for stream processing for handling events coming in from an external system, can be done with the same execution platform. So here was another problem we ran into with a cable system. That the challenge they had is they wanted to track all of the set-top boxes. They had about 10 million set-top boxes generating channel change events at the rate of about 25,000 per second, 2.2 billion a day. And what's interesting is they too have proprietary algorithms. Like they actually have a lot of secret code to determine when somebody is actually doing something useful versus falling asleep on the sofa by looking at the time delays and the repetitiveness of the channel changes. And so what they wanted to be able to do is take these channel change events and correlate them by cable viewer and match them up to programs, and within 5 seconds feed them to their in-house recommendation engine to recommend shows and advertising to the cable viewer. The problem was it was taking them 6 hours, and they were thinking about bringing in an in-memory data grid as a cache. And they said, we think we can get it down to 12 minutes. So I said, I think you can get it down to a few seconds, and if using data parallel computing. And so we had to prove that to them, which we did. Now, the other thing they want to do, besides looking at these channel change events, is they wanted to find aggregate patterns, both to see what are the most popular programs and number of viewers by, say, region or zip code, but also to look for things like service issues. Do we have a regional service issue or hotspots in their network? So again, we use the in-memory data grid, selecting the domain, which is an object per set-top box. And that object hosts information about the cable viewer, so their demographics, their history, the services they have with the cable system, the history of that cable box, did it overheat in the past, whatever, which model number it is, which version of the software it's running, et cetera. And so they would get these channel change events and be able to do this analysis and make recommendations and also alert their service people very quickly with this technique. And so we created a console for them as well and demonstrated. They're running on Amazon. At the time, we were running on 20 servers. And in fact, the one thing that they objected to is, why does it take 20 servers to do this? We had just chosen 20 so it would run super fast without having to think about optimizing it. We quickly optimized it down to about 5 servers. In any case, we were able to demonstrate 30,000 events per second and being able to look at all the viewers by most popular programs by zip code. That's for San Diego. And then also to drill down and look at all of the details about a given cable viewer. So what we're doing here is combining, I think I glossed over this, we're combining SMI to handle the events, single method invocation, and parallel method invocation to find the most popular programs by zip code. So this actually leads into some very interesting capabilities of combining data parallel computing with stream processing. And that's how you break the barrier of the Lambda architecture, right? The Lambda architecture is doing the stream processing. They can't do the data parallel computing. You have to push the data out and then go do that in the data warehouse. But in fact, if by using the domain that you create for stream processing, and here the set-top boxes, you can also do a data parallel operation on those objects while you're stream processing. And so you see there's some real power from that. Now, one of the problems that we learned from this example was the latency for doing stored procedures in a grid can be awfully high if all you're doing is posting events. So we added ReactiveX observers to reduce that latency. That's just something you might find interesting, that if you really want to work on the latency of getting an event or an invocation out to the grid worker and to get it executed, and the ReactiveX APIs and implementation in Java and C# turn out to be very well suited for this. So that leads to the next example. This actually came up last year at this conference when somebody was talking to me, and they came up with this problem, and how do you solve it? And so we spent a couple of months figuring out how to solve it. And again, it's another thing of what's the domain, right? So I don't mean to sound like a professor or something, but it's the same problem every time. What's the domain? So let's look at this. This is a financial services company that wanted to query. They needed to have thousands of clients querying stock prices for today and yesterday, and doing such things as currency conversions in real time. And so the requirements are that you have to be able to see all of today's and yesterday's stock prices, and yet you have to see the very latest stock ticker change. So like if it happened a millisecond ago, you need to see that. You can't see it like half an hour from now. And you need to be able to make this available to thousands of clients with hotspots, because some stocks like Amazon, everybody's going to query, and others like Scale-Out Software, if we were up there, they probably wouldn't query. We're not up there, we're not public. But you get the idea. So how do you solve that, right? So their solution had been historically to use they had 12 replicated databases. And the problem was they just couldn't solve the problem of how do I see the latest ticker symbol. And there was no way to keep this coherent so that all of the clients would see the same data. So it's a problem, right? So the solution we came up with was store 2 objects in the grid for each stock, so like Amazon. And you'd have one object has all of today's prices and is being continuously updated through ReactiveX event handling. The other one had yesterday's. Why 2 objects? Well, because what you want to do is cache those objects in the client systems, and you don't want to churn a lot of data with every update. So by separating it into at least 2 hours, this is a simplification. You could have 1 per hour for today, and as you finish an hour, they'll never change again. And so you want to have an object that's being changed, and then you want to have another object, hopefully that's not changing, because it's the updates won't affect it. And so this system allows them to have coherency. Every client sees the same view, and they have transparent scalability. And there's a third benefit, which we figured out, and this is another thing that we have learned in our history as a company, that usually when a customer has a problem, it's not a matter of, oh, here's the solution. It's like, well, here's the solution, but oh yes, I think you need a new feature. And so most of the features in our whole ecosystem have come from these kinds of discussions. And in this case, the feature was to implement a special read mode, so that when you do the CRUD read of an object, you don't have to wait if it has been invalidated in the client cache because a stock update came in. You just read whatever you have, and then you asynchronously update the client cache. I don't see that in any other product out there, but it's kind of an arcane niche feature. But if you think of the value that has, is that you do care about the latest stock tick, but if you're a human, if one comes in just before you're reading it, it's okay. You'll catch it on the next read. So this is an extension we made to our Java APIs to support this models, and that gives latency that's always predictable. You never have to wait and go back to the server to pull the data across the network. Okay, so that's another example of stream processing, and that gives rise to this notion of using an in-memory data grid more formally for stream processing. And so we thought a lot about that, and we realized this so-called digital twin model, which I'll talk more about tomorrow, and I've spoken about at previous conferences, it's a marriage made in heaven for in-memory data grids, because it's an object-oriented view of data by data source. And it's by having such a thing, you solve several problems. If you think about how Apache Flink or Beam work, or Storm before that, the problem they have is they don't have a data model. They have an execution model, which is generally a pipeline or a graph model, right? People think in terms of the data of the execution flow, not the data, the context. Well, the power of having context, we saw several examples. Let's think about the cable viewers. We're going to see 2 more examples before I wrap up after this. The problem you have is you're getting telemetry from data sources. Let's just look at this one here, and I'll come back to that. Like, say you have a fleet of vehicles, you're getting telemetry of all sorts, right? And you want to make sense of that telemetry to provide feedback. Well, you need context to do a good job. If you think about Flink, right, you get the telemetry or Spark streaming, and what you have at hand is the set of events that have been flying by. What you don't have is a natural way to hold context. For example, who's the driver? What's their driving history? Are they a speeder? Did they just take some drugs? Is the vehicle in need of maintenance? Is the guy appearing to be lost? All kinds of context that you can use when another event comes in to make a decision. A better example is one that this one I'll talk about here very briefly. I'm running out of time, so I'm going to skip around a little bit, which is what I prefer to do anyway, is if you have heart rate watches and you're monitoring people doing exercise, then if you know something about the runner, what their age, their BMI, if you know their medical history, and you can then make a much better decision about whether to alert them about a problem or to change exercise, right? So the context is vital. And people talk about having the context, but these streaming systems don't generally provide it. Well, the digital twin model, which was created for another purpose, for data modeling in general, building large systems like 777s, right? That's what the digital twin came out of, that world. But it can be applied to streaming analytics because it can encapsulate both the set of events for that data source and also state information about that data source, as well as the algorithms. Again, this is where you can encapsulate in an object-oriented manner the algorithms that you care about for this type of data source that can be highly proprietary. And with that, you have a much better context. It's solving several problems. It's giving you context you need for stream processing. It's also providing automatic correlation, because we can RX ship these events out to a particular object, so we're automatically correlating them. We don't leave that to the application to correlate. So hosting a digital twin model in a grid gives you a lot of advantages, not the least of which is scalability and high availability built into the grid. So turns out in-memory data grids are pretty good at stream processing. And this is one example we just looked at. Here's another example, and this is where we could take a look briefly at the fact that you could do data parallel computing at the same time that you're doing stream processing, so you can give feedback. Here's what everybody in your age group that's is doing right now. This is what their heart rate is. And in fact, if it exceeds some bound, you could say, "Hey, alert! You're like 30% higher than everybody we're measuring today at Orange Theory in your age group. So there might be a problem. You might stop." Stuff like that. So you could feed that to an analyst or feed it directly back. Now this is the last example, and hopefully I've left enough time for Oleg to do a very brief demo. We'll probably run right to the 12:45. Anybody's overly hungry, go ahead. E-commerce recommendations. We spent about 3 years looking at this problem. What's interesting about this problem is it fits the digital twin model very nicely. The goal is to help e-commerce shoppers find the product they're looking for. And the challenge is that most recommendation systems that you will run into, their goal is not to help you find the product you're looking for. Do you know what their goal is? Is to maximize the basket size, get you to buy anything, just buy something. So they're trying to understand about you, the so-called 360 view of the customer, because what they want to do is find out better ways to get you to say buy. But we thought, well, wouldn't it be nice to see if we could come up with an intelligent algorithm to, when you're on Amazon or something and you're looking for a certain kind of product with a certain feature set, to actually be able to find that product efficiently. And there was some work being done at Technical University in Germany that had actually studied this and found that if you look at the click stream and analyze it, you could do a much, much better job of doing recommendations. So we took that and went one step further by adding demographics of the shopper and what their shopping history, their favorite brands, all that is, and combine all of that together with a digital twin model to make real-time recommendations in under 100 milliseconds. That's sort of the industry goal. So this combines stream processing and data parallel analytics in the following way. So not only can you look at the blue is features that you want, but in addition, we can provide real-time feedback on what's selling best, what's most viewed right now by doing data parallel analysis of all the customers using PMI, while we're at the same time doing stream processing of their clicks and then provide recommendations. We also can roll that up onto with metrics on a dashboard for the merchandiser to see what are the most popular products, what are the most popular brands, and what are the sales today, et cetera. So it's all real-time analytics updated every few seconds, made possible by data parallel computing. And the domain here is the shopper, right? We're doing it across shoppers. And we're doing also the stream processing using this digital twin approach where each shopper is a digital twin object in the grid. So I'm going to do a quick wrap up and see if we can do a quick demo for you. So the challenge is that in-memory data grids have been thought of as caches. And in fact, they're a platform for doing data parallel computing of various types where you can consider stream processing another form of data parallel computing in order to achieve operational intelligence, better introspection, faster feedback, higher quality feedback. And what's interesting is an object-oriented approach, which is afforded by the in-memory data grid NoSQL view, object-oriented view of data, allows the user to encapsulate proprietary algorithms very naturally into the grid and view the grid as an orchestration platform for their algorithms to achieve scalability, high availability, and allow them to get this operational intelligence in with a very clean separation of concerns. So let's do the demo, and then while he's setting it up, I can answer questions. So any questions? We'll give him a minute on any of this. Yes?
I have a question.
You ready? Oh gosh, I guess I can't answer that, huh? No, real quickly, one of the things we do is have authentication per namespace in the grid. Another thing we do is you can have encrypted communication to and from the grid. And the third thing you can do is make sure you hide the grid servers behind us in a secure environment. So we have not attempted, we don't try to make our grid visible on the internet. We make the assumption it's behind a firewall, but nevertheless, they'll have those features and others, such as encrypted data within the grid, is very easy to achieve. Okay. That's a quick answer. Yes. All right, Oleg, it's all yours.
Okay, so I just want to show you the way how our grid is used for recommendation engine, and Bill mentioned that we spent 3 years of that. So in this case, all our efforts gets materialized in the protocol inside, scale out inside. So this is the console which shows you, I have a store in San Francisco here. And one of the misconceptions is the data has to be huge to do the parallel analytics and meaningful analytics in general. But in this case, we load. So in this case, we integrated with Best Buy dataset, and I load that dataset on my laptop here. So that's not a lot of data per se, but it's everything what you can find on the Best Buy. And if we go to the Best Buy website and we pretend we're a shopper, we can try to show you how we can help the shopper to find the product faster using the in-memory data grid. So for example, if we go to the, do the search, oops, let's do DSLR, for example. I want to find the best camera for my needs, so let me open the first one. Let's do that one. What we do, we try to watch the clicks which comes from the browser, of course, and you can imagine you have dozens of thousands shoppers at the site at any moment of time. So we solve two problems. First, we try to process the clicks from individual shopper and build the product set for them to match their interests by try to understand what the pattern of between those clicks, what kind of products shopper try to zoom in, what features he is looking or shopper is looking. At the same time, the second problem is, as Bill mentioned, we try to calculate the aggregates in the real time using all that data stored in the memory grid and see what is the most popular product right now and what is the best rated products, etc., and deliver that information also as a part of the recommendation stream back to the shopper. So if we look on the screen here, so we have little section here which we inject our UI widget to the real Best Buy site, and you can see based on what I start clicking, for example, this is all the recommended product. If I start clicking on the product which recommends more and more, we try to analyze all those clicks and give you the product of the same type. For example, the same pricing category, the same set of attributes, and then we visualize our decision. So, for example, let me click one more product, and then we visualize that decision based on the attributes we think are common among all those products you just clicked. So, in one of them, for example, you see, if I can go through the list, this is all the attributes each product has, and for example, one of them is the image resolution, and we also visualize, oh, this is the handy attributes, it's all cameras, you see how many are shared, and for example, if I want a camera with 4K video, this is precisely 4K resolution. Oh, that's not the image resolution, yeah, that is image resolution. Let's do, oh, that's image resolution, not video resolution, sorry.
Close enough.
Close enough. So if I want, for example, another type, and it gives me kind of the filter. And so in this case, what happens, it is kind of filtering on the top of what we already inferenced. So we already inference and give the set of products based on your pattern of your behavior, and then we allow you to zoom in on the top of that to the product you really want to see. Or you want to switch from the Nikon brand, you see the most of them Nikon. If you want to do the Canon, for example, you can zoom in and see, boom, this is all the Canons right there, and then you can explore the attributes using here, and we visualize some of those attributes, as you can see in the little menu, for you to see. Why we recommend actually, this is all the set of attributes which are common among the product you clicked so far in that category. And of course, if you switch to TV and another category, it's a completely different set of recommendation based on the attributes that category has. So that's in a nutshell how we can, and that's real time across all the customers which currently shopping on that particular website, and taken in consideration all the data we collect in addition to the attribute set which we have loaded from the Best Buy data set. So that's pretty much all.
That doesn't mean to imply that we're running on Best Buy. This is just a demonstration. We're not running on Best Buy. Don't look for us.
Yeah.
Okay, any questions? We're out of time. Feel free to jump up and go grab some food. Thank you very much, by the way.